And we should be recording. So before we get on to the skeletal system, which is the main thrust of today's talk, I did want to, because we ran out of time on Thursday, I did want to just mention the different types of skin burns really quickly. I'm going to do this quickly, but it doesn't mean that I don't want you to read your textbook. So that's always the disclaimer. We just simply don't have time to go over every single detail, or it would be a 2.5, 3-hour lecture 2 or 3 times a week, and we don't have time for that. So burns, anyway, burns of the skin. The main content of that is that burns of the skin denature protein. When cells are burned, highly heated to super high temperatures, that denatures proteins. I'm just letting another student in here. It denatures proteins and kills the cells. What that word means, denaturing a protein, or what that sentence means, denaturing of a protein, proteins have to be a specific shape, really, in order to function properly. And denaturing heat denatures proteins and makes them dysfunctional, usually by breaking chemical bonds and disfiguring them in some sort of shape. Now with skin burns, the major acute concern, the immediate concern, is loss of body fluids. So that's sort of the first thing to assess and also address in healthcare. If a person is burned, are they burned to the degree where they're going to lose significant body fluids? Because dehydration can kill a person. So the three, and I know you know this, but I'm just going to highlight them very quickly. The 3 classifications of burn are 1st degree, 2nd degree, and 3rd degree, based on severity in that order, with the first 2, meaning 1st and 2nd degrees, being partial thickness burns. So 1st degree burns affect almost exclusively just the epidermis, sometimes the upper dermis, but usually a 1st degree burn just affects the epidermis. A classic example of that is this, a sunburn, UV radiation, a typical sunburn. A 2nd degree burn, which can also come from UV light as well, it just means it goes a little deeper into the dermis. Usually blistering occurs. I'm still letting students in, which is why I keep pausing. Usually blistering occurs with a 2nd degree burn, but both 1st and 2nd are considered partial thickness burns. And a 3rd degree burn is a full thickness burn, meaning the entire skin layers all the way down deep into the reticular dermis is affected by that type of burns. And it's the most severe, obviously. Typically, a 3rd degree burn destroys nerve endings. So 3rd degree burns can often not produce a lot. They may not produce a lot of pain because nerves have been destroyed. There's also severe chance of loss of fluid, that dehydration concern, that acute concern, especially with 3rd degree burns. With 1st and 2nd degree burns, normal skin healing usually takes place, and that's sufficient to revive the affected area. But 3rd degree burns usually require some sort of skin grafting in order to prevent acute fluid loss, as well as healing and what regeneration and fibrosis is going to go on. Skin cancers, spend just a minute or 2 with skin cancers. There's 3 major types of skin cancer that affect humans anyway. I'm going to go in the order of your book. A basal cell carcinoma, this is by far the most common. And as the name suggests, it affects the cells in the stratum basal of the epidermis, mostly those basal stem cells and the young keratinocytes that were just newly produced by those stem cells. It is the least malignant of the 3 cancers, and it's also very slow growing. So there is a high chance of survival rate, especially with early detection with basal cell carcinomas. And with that particular cancer, the cancerous cells, the multiplying cells, the uncontrolled mitotic cellular dividing cells usually invade the dermis. They go downward into the dermis and hypodermis. But, and there's an ulcer that also appears on the surface of the skin. So with these skin cancers, I'm trying to get my fingers in view of the camera. With these skin cancers, the the uncontrolled cellular growth usually goes both superficially and deep, like my fingers are spreading apart. The major concern, obviously, is with the deep growth of the cancer, and if it gets into our body fluids, it usually can be metastatic or metastasized. So an ulcer typically forms on the surface of the skin with basal cell carcinoma, and the typical procedure of treatment is just excision or removal of that ulcer cancer. And once again, early detection is extremely successful in the curing rate. The second most common is called squamous cell carcinoma. And that usually is a cancer of, it has to be a living cell, but it's further more up in the level of the epidermis, more superficial, and in the stratum spinosum, not in the stratum basal. So in squamous cell carcinoma, it's those stratum spinosum cells that are affected and become cancerous. And the common most common sites of that squamous cell carcinoma are usually places on the head and hands. Those are the most commonly areas that are exposed to UV light on humans because we typically wear clothing. This cancer is very rapid in cellular growth. Unlike the basal cell carcinoma, the squamous cell carcinoma is very rapid in growth, and it has a little bit higher chance of metastasis, of traveling to another site in the body. Typical treatment is both excision, which means removal of the tumor itself, physical removal through surgery, as well as some sort of chemotherapy is usually indicated for that one. And finally, the third one, melanoma, or malignant melanoma, which is the most dangerous version, is the most dangerous type of skin cancer. It's a much lower percentage of types of skin cancer. It's only like 3% of all skin cancers are melanomas, but a much higher death rate within that small percentage. So it's highly metastatic. That means that the melanocytes that are affected, that are the cancerous cells and uncontrollably multiplying, typically get into the fluids and travel all over the body. This particular cancer, one of its secondary sites that it likes to set up shop is in the brain, in the central nervous system. And then those cancers just choke off the function of the brain. So obviously it affects the melanocytes in the stratum basal layer. And the appearance on the surface of the skin is typically a dark, blotchy, sometimes raised, irregular looking mole. And how dermatologists typically assess that is they look at an individual's overall population of moles on their body. And malignant melanoma typically looks unusual for that person in terms of color, if it's darker than the range of moles on that person, or it's more irregularly shaped, and also if it's quite quickly changing. That's sort of how dermatologists detect this type of cancer. The rule of thumb is if it's more than 4 millimeters thick when they do a biopsy on that type of cancer, then that's a really bad sign. It usually means that those melanocytes, those cancerous melanocytes, have metastasized elsewhere in the body. And the treatment for that is excision, which just means surgical removal, as well as immunotherapy, which is a little bit different than chemotherapy. So in 30 seconds, I know that some of you know this, but in case you don't, chemotherapy is just a poison that's injected into the body. And hopefully the poison kills the cancer before it kills the individual, the person. And that was the standard treatment for cancer for decades, has been. But more recently, immunotherapy, I know you haven't studied the immune system in great depth yet, but immunotherapy in 30 seconds, what that means is scientists take your own immune cells, your own T cells out of your system, T lymphocytes, and they train your T cells to recognize the cancer that's in your body. So let's just say you have a specific type of cancer. Immunotherapy usually involves taking your own immune cells out and then exposing them to the same cancer cells that are in your body, because a lot of times uncontrolled cancer, the problem is our own immune system doesn't recognize those cells as foreign, and so it doesn't kill those cells. So what we're doing is we're training our own immune cells to recognize the cancer that's inside of us. Then they multiply those T cells, those immune cells, and reintroduce them to the patient into their body. And now those cells will recognize the cancer cells, and they're very specific. They only go after those cells and kill those cancer cells. All right, so that's it with the integument. I'm going to call up my first whiteboard and start with the skeletal system, which is why we're mostly here today. So let's begin. I'm not going to be able to write every single word. I'm going to draw some pictures today that will help. If I write every single word out that I say, then we would be here all day. Obviously, that's no good. So the skeletal system, just so you know, first and foremost, includes both all of the bones in the human body as well as the cartilages that are associated with that system. And that can be any of those three types of cartilages that we learned in the tissue chapter. It can be hyaline cartilage, fibrocartilage, and elastic cartilage that are associated with the skeletal system. So those are considered part of the skeletal system as well. I'm not going to go into the specific tissues. We've already done that. Next thing I'm going to write is this bone classification. This is very easy and simple. Bones are classified by shape in the human body into one of 4 or 6 categories, depending on what textbook you have. And since your Marie book just classifies bones into 4 different categories, I'll use those 4 and not all 6. This is very simple. It's just based on what they look like. We have long bones, short bones, irregular bones. Sorry, I went slightly out of order. I think flat bones, your book does as number 3. So obviously this is just based on what they look like. Long bones, examples of that is any bone that is longer than it is short or wide. So things like, mostly in our appendages, we find long bones, like the humerus, radius, ulna in the arm, the metacarpals in our hand, as well as phalanges in our fingers, are all examples of long bones. The femur in the leg, the tibia and fibula in the leg as well. Short bones are bones that are just shorter than they are long. This includes things like wrist bones and ankle bones, like carpals and tarsals. Those are classic examples of short bones. Irregular bone, I'll do flat bones, since I'll give you some examples of those, since that I think is number 3 in your book. Flat bones are things like plates on the cranium, on top of the head. Those are very flat types of bones. The scapula, the shoulder blade in the upper back, is also a classic example of a flat bone. Irregular bones basically are any bones that don't fall into one of these 3 categories. Then we lump them into regularly shaped bones. Some classic examples of those would be things like, bones in the pelvis, as well as vertebrae in the spine. What you and I call the spine technically is the vertebral column. Those are very irregularly shaped bones and would fall into those categories. I'm going to list and describe, I won't write all of the descriptive words out, but I'm going to list the functions that your textbook lists of the skeletal system. Structure. The skeletal system gives our body an internal framework, enables us to sit upright, stand in conjunction with our skeletal muscles. That gives our body some sort of internal framework or structure. Protection is a big one. Classic examples of bones that protect would be the cranial plates on the skull, protecting the brain underneath, as well as the thoracic cage, which you and I call the rib cage, protects the organs below or deep to that, the heart, the lungs, etc. So we've got structure. I'm going to go in the order of your book. Number 3, I think they have movement. Bones themselves don't move, but they provide levers for skeletal muscles to pull against. So the whole, when my bicep muscle contracts, it pulls on my radius and ulna of my forearm, and my whole forearm moves. So that is what is meant by movement. Number 4, mineral storage. The two big ones. There's more in addition to these, but by far the two big ones are calcium and phosphorus that our bones store. Mineral storage. There's also some lipid storage. Triglycerides are stored in the shaft of long bones of adults, and I'll get into that later. So we've got mineral storage, lipid storage. This is a big one. Blood cell formation. In the spongy bone, and I'll describe what that is and where that is, we have red bone marrow. And so actually all of our blood cells are formed within bone tissue somewhere. That process, blood cell formation or blood cell synthesis, is called hemo or hemato, either one, poiesis. And finally, hormone production. It's not a major hormone. The bones are not major hormone glands or secreting, but there is minimal hormones. Example, osteocalcin, which participates in bone formation, is a hormone that is secreted by bone tissue. All right, let's move on to bone structure, which I am going to draw some pictures for you. Don't feel like you have to draw this. You can watch this as many times as you like. There are also great diagrams in your book. But if we start this from a simple page of a blank page, it helps simplify the process for most students. So I'm going to draw a generic bone here. This is not any bone in particular. I ran out of space down here. And we're just going to label some of these. It's just, think bone anatomy, a typical bone type of anatomy. I'll write the terms over here. The first one, that's pronounced diaphysis. That just means the shaft of a typical long bone. So the diaphysis of this bone that I've drawn would be, let's number these, would be here. And the next term, number 2, is epiphyses. That's plural. ES at the end means more than one. IS at the end just means singular. The epiphyses are the ends of a typical long bone, which is why we use plural, because there's 2 ends to the bone. And there's oftentimes, I'll just put a number 2 here and a number 2 down here. So what we say in the language is there's a proximal epiphysis and a distal epiphysis associated with the bone. So for example, I'm pointing to my humerus, my upper arm bone right now. The shoulder would be the end of that bone where the proximal epiphysis is located, and the elbow would be the end where the distal epiphysis is. Next word I'm writing is pronounced metaphysis. I'm going to write metaphyses as plural. This is just the middle between number 1 and 2. It just means this neck region here and here. And the only reason, or the biggest reason, that we bring up the term metaphyses in this case is in young individuals and adolescents, children and adolescents who are still growing in physical growth, in the metaphysis region, there's something called a growth plate, which I'll explain in great detail probably on Thursday. I'm just going through this, making a list of terms. A medullary, need to drop a student in just a minute, please. The medullary cavity, that refers to the center. In the center of a typical long bone is a space. So I'm going to put number 4 in here. This is the medullary cavity. And it's filled with what we call yellow marrow, which is fat or lipid in an adult. So I'm going to write yellow marrow, adult. And typically a medullary cavity is filled with red marrow in an infant. Red marrow is always the site of blood cell synthesis, of hematopoiesis. So in you and me, and fully grown adults, most of our long bones in the medullary cavity are filled with yellow marrow. In infants, newborns, it's red marrow. Okay. Next term, something called the epiphyseal line. On most adult bones, there is a scar, a line right in the metaphysis area that you can actually see on the surface of the bone. And what that is a remnant. It's a scar of where the growth plate was when we were young and has now fused bone on bone. So that's what the epiphyseal line is. It's a remnant of the epiphyseal growth plate, or what we could just call growth plate. A nutrient artery is the major blood supply to a typical bone. So it's not the only blood supply. So let's just say this is a bone in the body. Typically there's a major artery that enters right around the middle of the diaphysis, enters the bone, and supplies, then branches after it enters, supplies much of the bone with a rich blood supply. There are other arteries that also supply the bone. Typically there's a smaller one that enters the metaphysis area and the epiphysis area as well. But the nutrient artery is this one out here, number 6. That's the major blood supply. 7, and this one's important, periosteum. Peri means around, osteum means bone. So this is a coarse connective tissue that wraps around typically the diaphysis of a long bone. It can also be around a flat bone or differently shaped bone, but since we've drawn a long bone, I'm going to draw my periosteum. It wraps around the entire diaphysis, and it clings to that diaphysis with penetrating fibers. So I'm going to accentuate that by just putting these little fibrous needles into the surface of the bone. It would be like if the jacket or hoodie that you're currently wearing, or shirt, whatever, had little tiny needles that penetrated your skin to hold it on. That's sort of what this periosteum is. So it's coarse connective tissue, and it has all sorts of functions. It helps maintain this blood supply. It also allows for muscles to attach to the bone in certain places, as well as ligaments. So it provides a site for attachments, as well as a site for arteries, veins, and nerves to enter and exit the bone. I think this is getting close to the last of our terminology here. Endosteum. That means within the bone. It is a unlike the periosteum, which is thick, coarse connective tissue, the endosteum is thin, delicate tissue. It's usually only one cell layer thick. it's almost like squamous epithelial cells, but they line the medullary cavity. The endosteal tissue is a thin, delicate connective tissue that lines the inside of the medullary cavity like this. Now, quickly, I'm going to, on my diagram, just describe to you that there are two major types of bone tissue in the human body. We mentioned both when we did the tissues in chapter 4, but we really only looked at, I think I only talked about compact bone. So there's compact bone and spongy bone that makes up almost all of our bones. They have both types of tissue. Compact bone, so let me just write this. I'll talk more about these in detail. I'm just not want to mention them now so you have an idea of where they're located and a little bit of what they are. Compact bone is usually what you and I think of when we hear the word bone. It's that hard, super hard, dense material. That is found in the shaft, in the diaphysis, as well as a super thin coating around the epiphysis. So, and I'm going to draw a thin coating down here. On the inside of the ends of long bones is spongy bone. And it's these little tiny bone needles or spicules. So we have spongy bone under a thin layer of compact bone up here. So it makes up the bulk of the epiphysis, spongy bone, as well as down here. So that's where the two generally exist. If we had a flat bone and we cut it, and we sawed it apart, and you could look inside of a flat bone like this, there's a relatively thin layer of compact bone that surrounds spongy bone in the center. And spongy bone is where we find bone marrow. Okay, so I'm just checking my notes here to make sure that I covered everything. I want to talk a little bit about bone structure and detail compact bone and spongy bone. I'm going to call up a new screen. I'm going to add on to this one. Let's just say spongy and compact bone tissue. We'll do compact bone first. This is how compact bone tissue grows, really, how it's arranged. If we take a typical bone, and I'm going to erase this quickly after I draw it. If I take this bone and I cut it right here, transverse section, and then we look at the end that we've cut open, that's what I'm going to draw. I'm going to magnify it. So this is the end of a bone that we've cut. Now I'm going to erase this just so I can write some terms over here. In the center of that bone is the medullary cavity. So I'll draw that first. And since we are all adults, I'm going to fill it with yellow marrow, with lipid. So there's the medullary cavity. All of the stuff that's white on the outside of the medullary cavity and still inside the bone is hard, dense, compact bone. But it's a living tissue. It's not just plain white like this. It actually grows in these sort of ring-like structures, and they're not consistently round and they're not all the same size. But if we were to examine, especially with a microscope, this hard bone tissue, we would see this pattern appearing like this. I'm not going to go all the way around to save time. Then in the center of all of these rings that I have created is a canal. And it runs parallel to the medullary cavity. We call that canal the central canal. I'll write this stuff out. First, this term, osteon, O-S-T-O-N. Osteon refers to one unit of compact bone growth or tissue. So all of these circles that I've drawn are each an osteon. So it's just a unit of bone growth in compact bone. In the center of each osteon is something called a central canal. It's also called a haversian canal. And then inside of each of those canals are vessels, blood vessels mostly, and nerves. And they run parallel to the medullary cavity. Now, I'm going to need to blow up an osteon to get to the most of the rest of these terms. So if I take one of these osteons and I magnify it, so this is not a bone, it's a unit of bone growth. So I'm going to make it not perfectly round so that you can distinguish between, this would be an osteon that I have just taken from here and blown up, magnified. In the central canal would be arteries and veins and nerves. Since I already used yellow for the lipid, most textbooks use yellow for nerves, but I'm just going to put a green there. This is how compact bone tissue grows. There are little pockets or cavities in this hard matrix. Remember, it's a connective tissue that kind of grow in a circular pattern. Well, the cavities don't grow, but there's cells inside of each one. So let me draw a little osteocyte in there. And the little pockets or cavities that the cells live in are called lacunae, or lacunae, however you want to pronounce it. If I put an E at the end of it like I did, that means more than one, that's plural. If I erase the E and just say lacuna, I'm talking about singular or one. So I've drawn lacunae with osteocytes in them. That's where the living cells reside, and there would be more out in a ring-like pattern out here. That's how compact bone gets its typical growth rings of a tree look, and connecting these little caves or cavities are little tiny canals that connect one lacunae to another, like this. And they can run this way as well. But when we look in a microscope, that this is really what gives us the impression that we're looking at growth rings of a tree. So lacunae are cavities with osteocytes or living cells. I'm running out of space for my term, so I'm going to move over here. This term, lamellae, it looks like lacuna or lacunae, but it's a very different term. This refers to the ring-like pattern of compact bone matrix. So pretty much everything that's white in my pictures are different types of lamellae. And if you see a prefix before the word lamellae, they all basically mean the same thing. It means hard, ring-like bone matrix. But there are prefixes put in front of them, like circumferential lamellae. That refers to the hard bone matrix really around the outside of the bone. There's something called interstitial lamellae. That refers to the hard bone matrix found between these osteons, like in these little white spaces that I've drawn. But this is the most important part of that descriptive term, lamellae. It just refers to hard bone-like matrix that typically grows in a ring-like pattern. I didn't write this word out, so I'm going to. These small canals that connect the lacunae are called, I don't want you to think that arrow is going to this word. They're called canaliculi. That's just a Latin term for small canal. And that's how the living cells communicate with each other and with the blood vessels. So I've drawn these little tiny lines I've drawn out here would be canaliculi. I think that pretty much does it on terminology, at least that's important to me that you know. There are other terms like perforating canals. Really, that term perforating canal refers to branching off. I've blown up an osteocyte over here, but branching off of these central canals are perforating canals that take arteries and vessels to lacunae as well. All right, let's move on and compare that. So this is all that I've drawn here refers to compact bone. Now we're going to make a comparison, and I'm going to draw how spongy bone is arranged and how it grows as well. So I'll label this spongy so you don't forget, since we went to a new page. First, there are no osteons in spongy bone, so the bone does not grow in these units of bone growth. It does have things called trabeculi. These are small bone spicules or struts, needles, if you want to think of them that way. And there's also red marrow. There are canaliculi. There are lacunae with living cells in them. So there's some similarities and some differences. Major differences is no osteons, and the major difference is the presence of trabeculi and red marrow. So I'll be quick about this, but these, this is magnified a gazillion times. There are these small bone needles or struts that grow in what appears to be a haphazard arrangement, sort of like this, and it produces this sort of nest-looking network of tiny bone needles. So what I've drawn here are trabeculi. And before I go any further, just so you know, these little bone struts or needles are not haphazardly arranged. They specifically grow in the orientation of resisting stress in a bone. So remember, we find this stuff largely in the ends of long bones. In here, this would be near the joint, and a lot of weight is borne by our bones. There's a lot of weight bearing down on them, and these little needles grow in specific orientation to resist that stress or that weight-bearing load. Weaving around these little needles or struts are blood vessels, capillaries, and they carry nutrition. We also find red bone marrow in this space, which is a gelatinous, jelly-like material that has blood cell stem cells in it. So I'm drawing a complete picture of what spongy bone is, all the constituents of it. In these trabeculi, we do have, guess what? We have osteocytes living in lacunae, but they are so close to the surface that not many canaliculi are necessary at all. So there is communication between them occasionally, but most of them get their nutrition because they're so close to the surface of these trabeculi that they can get nutrition directly from that capillary spinning around through there. And finally, on the covering, on the outside of these trabeculi, let me write this, we find endosteal tissue, that thin, delicate, so endosteal tissue, or you could just say endosteum, covers the trabeculi. That's that thin, delicate connective tissue. That's supposed to be an E, trabeculi. I'll just mimic that by putting a little green. Let's use a different color because I used green for a periosteum. So I'm just going to use yellow. I'm limited with my colors. Covering the surfaces of these would be a thin, delicate connective tissue. So that gives you an idea of the differences between compact bone and spongy bone, a little bit anyway. Capillaries in the endosteum really supply the nutrition that diffuse from that capillary network to the living cells themselves. I'm going to explain to you now how cells, the living cells in bone really do their thing. So, oops, let's do black because it's easier to see. I'm going to list these in order that your book does. At least I'm pretty sure this is the right order. Osteogenic cells, also called osteoprogenitor cells, same thing. These are stem cells. They're bone stem cells that give rise to osteoblasts. Where these stem cells come from is mesenchymal cells, that embryonic connective tissue that gives rise to all types of connective tissue. So mesenchymal cells give rise to osteogenic or osteoprogenitor cells. They are stem cells that then divide and give rise to osteoblasts. We find these actively dividing stem cells sort of on the near the surfaces of a bone. So under the periosteum and also on the endosteal surface. So both on the inside lining as well as around the outside surface, we find a lot of these osteoprogenitor cells. And they give rise to a squamous looking cell that actually turns into an osteoblast. They also give rise to something called bone lining cells, which I'm going to define those two in a minute. Let's go on to our second cell type here, and I'm just going to make that an osteoblast. You already know the definition of that. That means an immature bone cell that usually secretes something. I'm not going to write everything out, but I'm going to say everything for you to help you understand it. This is an immature bone cell that secretes the organic part of bone matrix. And that organic part of bone matrix is called osteoid. Osteoid contains largely collagen fibers and other organic substances. So collagen fibers are part of the osteoid, that organic. It's kind of like a paste or a goo that's secreted by these cells. Here's how it behaves. I'm going to give you, I'm jumping ahead a little bit, but if this is an osteoblast, and it's a sunny day, so our osteoblast is happy, it secretes this stuff that we call osteoid, and it's not very hard yet. It's kind of like a goo-like material. It's organic, meaning it's carbon-based. A lot of it is collagen fiber. And how bone is formed is, if this is a blood vessel, a nearby blood vessel that has calcium and other minerals in it that we've ingested, like phosphorus, the calcium is brought to the area by the blood. We have to ingest calcium, we don't make it. And so the bloodstream brings calcium to an area, deposits it. The process of depositing calcium to an area is called calcification. So that's what I've drawn with my first arrow. Now this osteoblast is secreting its organic material, its organic stuff, and when the calcium and other minerals, by the way, mix with, it's a chemical process, when it mixes with the osteoid, it gets crystallized and really hard. That process is called ossification. And that means the formation of new bone tissue. So I'm just going to write bone. Really, it's bone matrix formation or synthesis. So ossification is slightly different than calcification. This calcification always is an ingredient in ossification. It has to precede ossification. This one means the formation of real bone tissue. This one just means the depositing of calcium in a certain area, usually where something like this is going on. Once that osteoblast, I'm going to draw it again over here. Once that osteoblast secretes its osteoid and surrounds itself with this organic stuff, and calcium comes in and calcifies the region and therefore ossifies this tissue. Now this osteoblast has sort of encapsulated itself in this hard matrix. When that happens, it stops secreting. It stops secreting the osteoid and it becomes a mature bone cell called an osteocyte. So let's go to that one next. So that number 3 on our cell list. This is a mature bone cell, and it was once an osteoblast, but it's no longer secreting that stuff, osteoid. It's a mature bone cell, and its job is to basically maintain that matrix that it's surrounded in. I'm going to write matrix / metabolism of that bone tissue. So the osteoblast builds the house around it, and then once the house is finished, it becomes an osteocyte that just maintains that house. We know now that these osteocytes live in little pockets called lacunae. That was created in the secreting process by the osteoblast. Number 4 on your list, I want to go in order, are bone lining cells. These are a byproduct, just like osteoblasts, of those osteoprogenitor cells, those stem cells. These are flat cells that are typically found on the surface of bone where active remodeling is not going on. They're also called periosteal cells. So I'm going to write flat, found on the surface of bones, usually underneath that periosteum. What remodeling means is the process of taking away old bone and making new bone. And it's an active process, but where on a bone that process is not going on is where we find bone lining cells. It sort of maintains that surface of the bone area, helps maintain the matrix on the surfaces of bone that are not actively creating new bone. And finally, number 5 are osteoclasts. It looks like osteoblasts, except it's a C instead of a B. These are completely different cells. Think of them almost as the opposite of osteoblasts. First of all, they don't arise from, I'm trying to go back, sorry. They do not arise from these stem cells. Osteoclasts do not. Osteoblasts do, as well as bone lining cells. These are derived from monocytes a monocyte is a type of white blood cell. And monocytes are also the synthesis, the derivation of macrophages as well. I think we said that a couple chapters ago. But when a group of monocytes sort of lump together, they have the ability to create these big cells called osteoclasts. Here's what they are and what they do. So they're large because they're a conglomerate of many monocytes. As many as 50 monocytes may group together to form these cells. That's how big they can be. They tend to be multinucleate because of the fact that they're from multiple cells. They have more than one nucleus. But here's really what they do, their function. They secrete lysosomal enzymes, digestive enzymes, and acids that dissolve or degrade bone matrix. So that's why I said picture them almost as the opposite of osteoblasts. Osteoblasts make new matrix, osteoclasts dissolve that matrix. So really quickly, in about 60 or 120 seconds, why would we ever want to dissolve bone tissue? Here's the gist of that story. Our bodies don't make calcium, but we need calcium to perform many, many vital activities in the human body. Every time a nerve cell fires, we need calcium to transmit that impulse. Every time a muscle contracts, we need calcium to perform that contraction. Every time your heart beats, we need calcium. Calcium is actually the most used ionic mineral in the human body, so we need tons of it. Because we need calcium all the time, and we can't be constantly ingesting it, we store over 99% of the body's calcium is stored in our bones. So, but when we put calcium into the bone for storage, we put it under lock and key. The calcium that we can actually use to do all those things that I've listed is calcium that's in the blood. So a tiny bit of calcium is always in our blood at any given time. And that's what our cells can use readily. When these levels, even though it's a small amount, when that level is strictly regulated, and when it drops, we can unlock this stored calcium from bone matrix, and it can diffuse or be dumped into the bloodstream. So we need these cells in order to dissolve this locked up calcium and release it into the blood. That's the benefit of these osteoclasts. They perform a process that is called bone resorption. You'll see that term in the book. That basically means this, dissolving bone matrix in order to release calcium and other minerals as well, but the big one is calcium. All right, so that goes through all the living cells. We're getting close to the end today. I do want to highlight this to you. I want to make sure I say the right table number. On table 6.1, or within table 6.1 of your textbook, it's a table called bone markings. We're going to apply most of that business to the next chapter when we study individual bones. So I don't mean to be, I am sort of skipping it on purpose for now. I will call your attention back to it when we get into chapter 7. Quickly before we leave, I'm going to discuss the chemical composition of bone. This is the chemical composition of bone tissue, really. There's an organic component and an inorganic component to bone tissue. Within the organic component, there are compounds. Let's just write the constituents. Organic, this would include all of the living cells, and it would also include the stuff secreted by those osteoblasts. So I'm going to write osteoid, and in parentheses, like 60% of osteoid is made up of collagen fibers. There's also glycoprotein, so I'm going to put a comma in that mixture. Organic mixture are glycoproteins. And then the inorganic compounds would be the minerals. So I'm going to write salts, we call them, because that's the chemical form that they're in. Specifically calcium and phosphorus. So I'm going to write calcium phosphates. I'll list some of the other, those are the two major, calcium and phosphorus are the two major minerals, but there's also magnesium in smaller quantities, potassium, manganese as well. This inorganic stuff is what gives bone its hardness. And it's largely this that gives bone, specifically these, gives bone its flexibility. So bone, believe it or not, as hard as it is, and you and I think of it as this super rigid, hard material that can't bend, or if it does, it'll break. That's true to a degree, but on a microscopic level, that's not really true. Inside of a bone are spiral-shaped collagen fibers, sort of like rebar going through concrete, that allows a bone, believe it or not, some flexibility. And really, it's within collagen fibers, we have bonds, chemical bonds making up those fibers, and we call them sacrificial bonds. Break on a microscopic level when a bone is stressed. We don't even know it, that this is going on. But if you bang into something really hard, or if there's a lot of force put on one of your bones, the first thing that happens is some flexibility occurs, and at a microscopic level, bonds within those collagen fibers are breaking to allow that flexibility. Those bonds are easily repaired, and we don't even know really that we've had injury. Obviously, if there's enough trauma or stress put on a bone, then we do actually get a fracture to that hard matrix. But the point is, this organic stuff gives bone flexibility, the ability to bend a little bit, and it's those sacrificial bonds of the collagen fibers that allow that to happen. I'm going to mention, I need to skip onto, your book goes into endochondral ossification and intramembranous ossification. Those are kind of detailed. I don't want to start that at this lecture point today. So I'm going to review to you how a growth plate works, which is skipping ahead one section, and then I'll come back to those embryonic ossification topics at our next lecture. So before we leave, I'm going to write an epiphyseal plate, and this is a growth plate. It's found in the even though it's misleading, even though it's called an epiphyseal plate, it's found in the metaphysis area of the bone. We've all heard of growth plates. Now I'm going to show you what one is and how it works. So I'm going to draw my picture over here. This is in a young person, either a child or an adolescent that is not fully grown. I'm going to draw a generic end or epiphysis to a bone. And I Didn't mean to draw it quite that with that. I'm going to cap it off here. So this is bone tissue. This is a young person that I'm drawing. And I'm going to write epiphysis. It's bone. Then there is a hyaline cartilage plate, and I'm exaggerating the length of it so we can identify all the regions of it. That is the epiphyseal growth plate. It is not bone tissue, it's hyaline cartilage. So I'm just going to write, this is the epiphyseal plate, and it is made up of hyaline cartilage. And this is how a bone grows in length when we're still growing. Down here would be the diaphysis of the bone. So this is all bone tissue. Within this cartilage plate, and I'm going to outline it in blue so that you remember it's hyaline cartilage. Within this growth plate or epiphyseal plate, there are specific zones of cartilage activity, and we labeled those zones based on what they're doing. So the easiest thing to do for me and for most, when I teach in person, I have students, I require students to draw this and explain it as an essay question on the exam. So you consider yourself lucky, you don't have to do this, you just have to know the information. I have them draw 3 lines in the growth plate that separates this piece of cartilage into 4 zones. And they're literally called zones for the name of what's going on in them. So I'm going to label them 1, 2, 3, 4. And there's a 5th zone down here that we're going to mention, which is actually in the diaphysis. So I'll name them and describe what's going on. The first one, different books call this a different thing. Your book calls it the quiet zone. Some books call it the inactive zone. Same thing. It gets its name because there is no activity, cellular activity going on in that zone. That's why it's called the inactive or quiet zone. So we have no chondrocyte or very little chondrocyte or chondroblast activity, cellular activity in that area. It's sort of like just this inactive hard plate. The next zone, number 2, is the opposite. We call it the proliferative zone. Remember, this is cartilage, not bone. And so in the proliferative zone, here in the quiet zone, I'm just going to write no chondroblast activity. There's really very little cellular activity going on at all. In the proliferative zone, it's the opposite, high chondroblast. That means immature cartilage cell that's secreting matrix activity. So we have new cartilage matrix being laid down here, new cartilage growth. And what happens is zone 2 pushes up on this plate. So the new cartilage growth, sort of like the skin, the epidermis, pushes upward like this, and that pushes the epiphysis away from this plate. Number 3 is called the hypertrophic zone. Hypertrophy, trophic, I want to make sure I spell it correctly, hypertrophic zone. What's going on here is old cartilage cells, they blow up, they enlarge, and then they die. So old chondrocytes, that's what a cartilage cell is, they enlarge and they die, and they leave cavities in the space in this area. They literally swell, kind of blow up, and then apoptosis, they self-destruct. And number 4 is a calcification zone. In this area, blood vessels kind of invade this area. It's high vascularity. And blood vessels bring cartilage to that area. So we have a large amount of blood vessels. They bring calcium to the area, lay it down for calcification, for the preparation of new ossification. And finally, number 5 is technically not part of the growth plate. It's down here. I'll try my best to squeeze this in. It's called the ossification zone. My page cuts off right below where I'm writing. That's actually on the diaphysis of the bone. The ossification zone is just where new bone is formed. So we have a high osteoblast activity. So I'm going to draw an arrow up. High So in essence, where new cartilage cells are growing is right here. And they're pushing upward all the time on this cap. And that pushes the epiphysis away from the diaphysis. The older cartilage cells, since growth is going in this direction, the older cartilage cells back here, they blow up, they enlarge, they die, leaving cavities and spaces in that area. Blood vessels invade that older area, lay down a bunch of calcium, and there's a high osteoblast activity coming up this direction. And so new bone tissue kind of gobbles up old cartilage tissue down here through the process of true ossification. And this high chondroblast activity keeps pushing up on the epiphysis. What makes it stop is hormonal signals during puberty. When we get at the end of our growth spurt, whenever that is, in our mid to late teens, chemical hormonal signals, what it does is it shuts off this. Hormonal signals shut off the new cartilage activity. And so this being pushed away stops. Osteoblasts keep gobbling this up even after the new cartilage has stopped, and we seal bone on bone at the end of our growth spurt. And that's what creates that epiphyseal line, that scar, that seal of where this plate once existed. All right, guys, we made it to the end today, so I'm going to stop my recording and then I'm happy to take any of your questions.